please take it away.
Okay, thanks for the next introduction from Rohan, and also thanks Andrew inviting me here. So Chuang, so I'm very excited to share our team's recent work on audiovisual signal analysis. So I mean, training deep learning that actually end-to-end has railroaded many real-world applications, including object detection, video recognition, motion translation, as well as speech recognition. And some of the recent systems have even achieved, that kind of performance, even beat of that of human. And on basis of this success, and it's tempting for us to think that deep learning might already achieve human-level intelligence. But there are also several technical reasons for us to resist this temptation. I mean, first, deep learning is always data hungry and require massive label data for model training. And second, they always have a limited ability to adapt and generate new concepts and new scenarios. And this system actually works quite different from human intelligence in terms of data efficiency, flexibilities, and generalization. And here I would like to show a video about how a baby is learning about the world. So in this video, it seems doing something a little bit random. He bring up he bunking up together, making stack and knocking them, and hear the sound. And there might be a few things that her parents, he taught them before, but most of the he's learning in his own. And he can leverage all the signs to figure out how the things works, and he can associate how the cow look like with how to feel, and how to feel with how it sounds. Essentially, he's trying to build a causal model of the world and to plan what has happened, infer what is about to happen, and then plan his action accordingly. And also, there's also intensive experience from cognitive science and also development psychology that indicate that the human can naturally attend to multisensory cue, and also their temporal coincidence to arrive a rich understanding of the physical event and also human activity. However, in AI, much more attention has been paid to how a single model can drive learning. For example, today's computer vision system, video recognition, image recognition, and also place recognition most focus on using visual signal line. And the natural question, I think, also in this workshop, that how we can inspire from the human ability to integrate multisensory data and leveraging the natural synchronization of visual and audio signal and enable AI system to learn more from fewer data. So the first application I want to talk with about visual sound separation. This is joint work with Dr. Heng Zhao and Professor Anton Torba at MIT. And I know that a bunch of organizer in this workshop, including Andrew Owens, Rohan, and also I know another after me also we also talk about this application. And one difference from them is that we mainly focus on music domain. The problem is that given music performance video like this one, and we aim to separate the sound source played by different music, different musicians. So let's first have a quick preview how audio-only perform this kind of sound separation. So they usually do is that they're using a model to first estimate a mask for each sound component, and then they multiply the mask on the input sound spectrum to separate the sound source. The audio-only works very well for them for some speech separation as well as music separation, but it's still quite hard to generate some very challenging and also natural sounds such as some music performance video. And to solve this problem, our idea is that we're trying to connect vision with sound by learning from the music videos. So we believe that a machine that can learn to associate the sound component with visual signal by watching and listening to many music performance video. So to this end, we first create a large-scale music video performance data set. It contains around 1,000 video. Over 20 instruments, and we make this data set publicly available. Feel free to use that one. And the core idea of our approach is that we first create a synthetic training data by mixing arbitrary sound source from different video clips, like this one. And then the objective of our model is trying to separate the audio track from the mixture conditional on their corresponding visual input. So even though the neural network is trained in a supervised fashion, it does require a lot of labeled data. So training pipeline can be then considered as a step supervised learning, and we also name this training procedure as a mix and separate framework. And this mix and separate framework is composed of 3 components. One is the video analysis network, the second is the audio analysis network, and finally is the audio synthesizer. So the pipeline works in the following way: that you first apply a video analysis network that can try to extract the visual feature from video frame that contains the musician playing instruments. And then for the audio network, we first convert raw waveform into sound spectrogram, and then using a unit style and architecture to encode the audio feature into different channels. And the audio synthesizer network then predicts the sound by taking visual feature and audio mixture feature as an input. And the learning objective is to estimate mask. And the ground truth mask for each video actually can be calculated whether the target sound is the dominant component in the input and mixture sound on the magnitude spectrogram. So finally, the predicted mask can be thresholded and multiplied with input complex sound spectrogram to get the predicted sound spectrogram. And we further can apply an inverse at TFT with the same transformation on the predicted sound spectrogram to reconstruct the raw waveform of separate sound. So in the testing, you can either take the raw video as input, separated corresponding sound, and of course, also you can collect the pixel and take the region feature as input to hear the sound. Here are some demo video that, for example, was the input look like this one. And this system can take the pixel. For them, you can take the pixel guitar, and here's the sound. And also you can, train another pixel and see what happens. And you might be curious, how about you clicking the pixel of the background? For them, you click the pixel of the hook shell. Okay, it seems nothing happened. So this means that this system, our system even trained without any label, it can learn to associate the sound component with the visual pixel, and also identify which region makes sound and which region might not. Here's another example. And we click pixel of 20. And also you can try the guitar. No, and again, we can also click a piece of the background wall. This thing works pretty reasonable well. And also, this system will also open up some new opportunity on the sound editing in video. For example, you can do the volume adjustment for specified musician, or even you can remove the audio from particular sound source. Here example. And you can adjust the volume of the first instrument and make another one sort of smaller. And of course, you can also do the reverse. So even though very impressive performance that this how sound of pixel and later sound of motion system achieved. So this approach almost built on the appearance of the full like the motion feature. It has limited ability that to find the correlation between audio signal and the visual point actually. So it's especially when separating the multiple instruments at the same time, like this example. So it's clearly in this changing case, I mean, the previous model did nothing, I mean, essentially. And to solve this problem, our idea is trying to using human body language that what we call the music gesture that can provide strong visual signal to guide the sound separation. So music gesture is a key point-based structural representation. And our idea is that based on the key point coordinate change over time, we can implicitly capture the body and the finger movements of the musician when they perform the music. And using this kind of point information, it could be possible that for us to doing more changing case. Here I will show some qualitative comparison results. And the first result we are generating by a previous solar system name of sound of motion. And it seems that this system did nothing in this case. How about the music gesture? So even though the system is not perfect, but it's a reasonable good performance in this very challenging case. Now here's another example. So again, the sound of motion system did nothing. How about music gesture? So I will show the last example actually I like most about two people playing the piano duets. And again, nothing can be done for the sound of motion system. How about music gesture? Yeah, it seems to work pretty well. And this kind of implicitly body motion also enable us to open some new application that, for example, we can separate music, perform music of multiple instruments. Most example I showed before about two different people play instrument, but how about we move three, move to four, and even more. So we're also doing some visualization of the key point attention map to understanding what this model actually learned. So we have some very interesting observation. Furthermore, we find that the model actually tends to focus on the hand key point when it separates the guitar and the flute sound, while they pay more attention to the elbow when separating the cello and the violin. So that totally makes sense because this is really the point of when musicians playing the instrument that make the sound. And at the end, I will show another interesting example that a musician actually make two different sounds. And our music structural system can also separate sound of upper and lower body of upper and lower body parts. So till now that we have seen how sensing human can benefit the visual sound separation. The natural question you might ask that have we directly generating a piece of music according to body movements? Like this one. So actually generating music from video is a very challenging problem. And I mean, because you first need to recognize the physical interaction between instruments and musicians from video. And secondly, you need audio representation that respects the major music rules, that so that it can be easily predicted from vision. And finally, we also need a model that to associate the two modalities. And our idea to drive the challenge is that we found two key elements for successful video to music generator. For the visual perception, we again using the key point, to model implicitly a body parts and hand movements. And for the music, we propose using MIDI, the symbolic music representation. So you might be curious, what is the MIDI? As MIDI events encoding timing and loudness information about each note event, such as note on, note off, then given a pair data of body key point and MIDI event. Music generation from video can be easily posed as a motion to MIDI translation problem. And concretely, that our pipeline works in the following way: that we first detect key point from video and apply a graph network on the key point to capture human body motion, and then we're using a transformer to align the key point feature with the MIDI event. And finally, the MIDI event is converted to waveform with a standard audio synthesizer. And here I will show some music generation results of our system. Here's an example. So since this MIDI representation is fully interpretable and transparent, it also enables us to do some music music style items easily. So then we can adjust the key of the generation. Here's another example. Okay, so in the first half of my talk, I mainly talk about how the audio visual learning from video, and in the same part, I would like to talk about the next step that we are I think our team thinks is important, is how to teach an intelligent agent that equip the camera and the microphone to interact with the environment and find the sound source in multiple environments. This is probably named as the audio visual embodied navigation. And we did some preliminary work in this field back to 2018 that we using AI 2000 and reason audio API into Unity game engine to simulate the sound effect. And basically that the agent can using camera and microphone to interact and find sound source. So the visual thing that we using as this early work that we using some scenes from the AI 2000, and also we make some apartments for more rich visual understanding. For the audio engine that we using open source Reason Audio API, that's similar to the later work that I think in the Christian Kurman team that also doing something very similar. That basically you have pre-record sound using the Reason Audio API. You can simulate the sound wave that receive at different location. And here I will show a demo about the data set look like. And since time is limited, I might not go to the detail. So the environment will look like this one. So I think that I think I will spend another 2 or 3 minutes that to talk about what I think might be important for the next step. For the audiovisual scene understanding from my perspective. So long-standing goal of AI is trying to engineer the machine agents that can interact with the world. A wider say to the house and also space. But such AI system must to pursue understanding. It's most about the physical world around them. We need to understanding why. The underlying physics for visual and audio generation. And when we understand this kind of physical term, it could be possible for our to manipulate object and form plan to execute the task. So because correct training this kind of multimodal real-world robot application is very expensive and also involves some safety risks. So there also be a growing interest in 3D simulator. To benchmark the embodied AI and robot learning model. So we joined this effort to building a general purpose world simulator called 3D World, or in short, the TW. Actually, this is a multi-modal platform for interactive physical simulation and built on top of CDR game engine of Unity. And basically, Unity handles the image and the physics rendering for us and allow for a range of user applications, including multimodal physical scene understanding and multimodal robot learning. And Jeremy and Sales, they are the leading engineering, building the platform. And last year, we made strong push to open source the platform. And you might ask the question that, there's also a bunch of other simulators, including Habitat, AI to Gibson, Virtual Home, or Sapien. So what's the difference of TW? So I think that in summary, TW has 3 unique features. The first is really highly flexible and general design. It can accommodate of a set of key applications, including multimodal perception, physical scene understanding, robot interaction, with the goal that enable training each of its applications using a single simulator. And secondly, I think the most benefit for this workshop communities that you support both visual and audio simulation. Will allow you to create the synthetic image data set at near photorealistic level and coupled with impact sound at high level acoustic fidelity. Then the TW also have advanced physical abilities, allowing both rigid body, soft object, and the fluid to interact. So the user can affect object by directly using AI API command, and also they can also using embodied agents as well that you can use in VR to pick out objects that from multisensory to interact with this object. So I will mainly talk about the multimodal data simulation part because this is the most interesting to the community. The KW essentially have a 3D site library that highly customized for research purpose. You can then run 200 objects, spanning 200 categories, and it also supports the physics and the material behaviors that can accurately simulate how the same object physically interact with the world, including generating the physical correct impact sound. And the model that also normalizes and also align with the worldness, the category. So here I will, I will show some example of this. So there's a generated simulator. For them, this is the high fidelity, visual scene, and we can do both. About inter environment, outdoor environment, for the photo release support. And also, it can also populate with some physical object that can support rigid body and soft body physical simulation. And the most importantly, actually, this is the leading. It also has a unique feature that is about impact sound synthesis. That this product can generating high fidelity acoustic rendering fidelity, including full audio spectral agent reverberation model. And the Pi Impact actually is developed by the James Tracer, that is also keynote speaker in this workshop. And they did wonderful work that can generating plausible and also releasing impact sound in real world time. in real time based on the mass and the material of colliding object, as well as the parameter of collisions as object velocity, angle of impact. So here I will show some example about this physical data side. Sorry. Let me play the video. So we are halfway that to building an embodied AI task that to do this kind of physical object localization that incorporate a real robot that trying to finding a foreign object in the scene. So we believe that next step for the audiovisual scene understanding is to incorporate the physics. To understanding how the visual and audio signal is generated from a physical process. Okay, I think I'm a little bit over time, and I would like to take some questions. Yeah.
Yeah, thanks so much, Chuang. Yeah, so very nice presentation. So if anybody has any questions, feel free to just unmute and ask directly or post in the chat. Yeah, maybe I have a question for the audio kind of physics-based audio rendering part you just showed. I wonder, is it more about materials, or actually is shape or 3D shape important for those objects when it impacts?
Yeah. So that actually is this is a good question. So when we generating this, the Pi Impact API actually developed mainly by the James. Actually, it supports both object mass, material, as well as the shape, and also thereby velocity, angle, and also some physical prep from them. When the because the difficult that trying to understanding that exactly that when the physical interaction happen and how they will align with the visual signal. So but in terms of the so short answer that when you do the sound generation, you indeed care about the 3D shape, mass, material, physical interaction. But when we have doing some experience, for example, based on this audio, trying to imagine object mass, falling height, or even shape. So we feel that the shape does not matter so much. For the kind of impact the generation. If you for them, we do some human study that as a human to tell the shape is not that easy. But for material and object size or falling height, actually people have good estimation from this kind of impact. So
yeah, thanks. Got it. Any other questions from the audience? Yeah, maybe one more question. Yeah, I think you showed a lot of work on audio-visual source separation, and you also mentioned that it's mainly about like speech and music. So do you think is there a reason for that, or kind of what do you think would be the next for audio-visual source separation? Is kind of to expand to other kind of different types of objects, or what's your thoughts on that?
Yeah, this is a good question. So so our team mainly working on the music domain. And we still think that, so for example, if you want to separate, there's still a richer application in the domain. We think we are still far away to solve that one. For example, if you want to, there's multiple person playing instruments. Over 3 or 4, and in some web setting, and also in some outshores that there's many people that you can do some group sound separation for them. There are some people playing violin, some people playing flute, people play other instruments. So how can you from this kind of very complex micro sound to doing some sound separation is still open research problem. And currently we haven't realized any model can doing some preliminary result in this kind of training setting, but it's reflect some real world application. Because for example, I think last year there's a company and also some outshore that reached out to us that they told us that for the education, for the education purpose, they have rich application that if you can doing the sound source localization, sound separation. So I think, yeah, I think natural sounds, for example, egocentric or natural sounds is a very interesting domain. But in terms of application domain, I still feel that speech and music might be the next few years that both for the industry I mean, so we still need to make strong push in this domain, and also fundamental progress that need to be made in terms of model architecture or training algorithm that many fundamental. I mean, it's still too early to say that this field, I mean, is almost solved. Yeah, it's my perspective. Yeah.
Okay, yeah, thanks again. Yeah, I think for the sake of time.